Assalamu alaikum wa rahmatullahi wa barakatuh. This is the second video of part 2 of chapter 10, Alternating Sinusoidal Current. At the end of this video, you should be able to compare the current in a coil to the alternating sinusoidal voltage across its terminals. First, let's remember 1. The expression of the maximum voltage is UM equal SV multiplied by Y, and of the effective voltage is U effective equal UM over radical 2. 2. The expression of the period is T equal SH multiplied by X, and that of the frequency is F equal 1 over T. 3. The expression of the phase difference between two signals is phase A with respect to B equal phi A minus phi B, where phi is equal to 2 pi d over x. If the phase difference of A with respect to B equal to 0, then A and B are in phase. If the phase difference of A with respect to B greater than 0, then we can say that A leads B or B lags behind A. 5. In RR circuit, the voltage and the current are always in phase. The voltage across a resistor is the image of the electric current since U equal Ri and R is constant. Introduction: Inductance of a coil. The self-flux through a coil forms the basis of the definition of a physical quantity called inductance. Let us first study the characteristic of the self-flux created in a coil by the current traversing it. Consider the following figure, which represents a coil, and the positive direction is chosen clockwise, so N is directed inward. For I greater than 0, when the current traversing the coil with the positive direction, that's mean, according to the right-hand rule, the magnetic field created by the current is inward. So, the normal vector of the coil and the magnetic field have the same direction. Then, the self-flux, according to the formula of the magnetic flux, is equal to NBS cosine theta, where theta is the angle between N and B. In this case, theta is equal to 0, so cosine theta is equal to 1, then the self-flux is equal to NBS, which is greater than 0. So, when I is greater than 0, then the self-flux is also greater than 0. Let us study the second case for I less than 0, when I is traversing the coil in opposite direction to the positive direction. That's mean, according to the right-hand rule, the magnetic field created by the current traversing the coil is opposite to the normal vector of the coil. So, the expression of the self-flux becomes NBS cosine pi, where cosine pi is negative, minus 1. So, the self-flux is equal to minus NBS, which is less than 0. That's mean, when I is less than 0, then the self-flux is also less than 0. So, I and the self-flux have the same sign always. And B, the magnetic field created by the current traversing the coil, is equal to mu0 NIL, where mu0 is a constant, N represents the number of turns of the coil, L the length of the coil, and I represent the magnitude of the current traversing the coil. So, the self-flux is equal to NBS equal N multiplied by mu0 Ni over Ls, where the self-flux and I are proportional, since N mu0 Ls are constants. Then, the self-flux and I are proportional and of the same sign. So we can replace the constants in the expression by L. So the self-flux is equal to Li, where L is the inductance of the coil, L is a constant and greater than 0. So the final formula of the self-flux is equal to Li, where the flux is in Weber and I in ampere, and the SI unit of the inductance is Henry. Expression of self-induced electromotive force. A coil of inductance L and traversed by a current I is the seat of self-induced EMF E, and according to Faraday's law, E is equal to minus d phi over dt, where phi represents the self-flux. And since the self-flux is equal to Li, so E is equal to minus dLi over dt. For a coil without soft iron core, which is a characteristic of a coil, L is always constant. And when the coil is with soft iron core, L is variable. Most of the cases that we are going to study, the coil is without soft iron core, so L is a constant. Then the expression of the electromotive force E becomes equal to minus LdI over dt. And the SI units of E is in volt, I in amperes, L in henries, and T in seconds. And we must notice that since L is positive, E and di over dt have always opposite signs. Ohm's law applied to a coil. Consider a coil of inductance L and resistance R, traversed by a variable current and oriented positively from A to B. The positive direction chosen is independent to the direction of the electric current. So, the potential difference across the terminals of the coil is UL, which directed from A to B, that's mean we are measuring UAB, is equal to Ri minus E, which is equal to Ri plus LdI over dt. So, according to Ohm's law, the voltage across a coil is always equal Ri plus LdI over dt in the positive direction. RL circuit experiment 2. Consider the following circuit, which contains a low-frequency generator that delivers an alternating sinusoidal voltage, a coil of inductance L and internal resistance R, and a resistor of resistance R. And the channels of the oscilloscope are connected as shown on the figure, where channel 1 Y1 measures the voltage UAB across the coil, while the channel Y2 measures the voltage UCB across the resistor. And we press the button invert on the channel Y2 in order to measure the voltage UBC, not UCB, since the positive direction chosen in the circuit is from B to C. So, channel 2 represents the voltage across the resistor, which represents the image of I the current traverses the electric circuit. According to the oscillograms, the two waveforms have the same frequency and same period. Thus, they have the same angular frequency, where UAB represents the red waveform and the blue waveform represents the voltage UBC. And according to the observation, the two waveforms are not in phase, and UAB reach the maximum before UBC. So UAB leads UBC. And as we said before, UBC, the voltage across the resistor, is the image of I. So UAB leads I, and then we can conclude that the voltage across the coil leads the current I traverses the coil. Analytical study. According to this study, we are going to show that the voltage across the coil leads the current traversing the coil analytically. Suppose that the current flowing in the coil is I equal Im sine omega t, and the voltage across the coil according to Ohm's law UAB is equal to Ri plus LdI over dt. Then, by replacing the expression of I and the expression of di over dt, the voltage across the coil UL becomes equal to Rim sine omega t plus L omega Im cosine omega t. Case 1, purely inductive coil where R is equal to 0, the internal resistance of the coil. In this case, the voltage of the coil can be written as L omega Im cosine Wt, and this expression can be written in the form of L omega Im sine omega t plus pi over 2. And by comparing the two expressions of I and UL, we can conclude that UL leads I by pi over 2, where the phase difference of UL with respect to I is equal to pi over 2 as shown in the expression. And the amplitude of UL is equal to UM, which is equal to L omega Im. Case 2, resistive coil, where the internal resistance of the coil is different than 0. For this case, the expression of the voltage of the coil UL can be written as UBM sine omega t plus phi, where phi represents the phase difference of UL with respect to I. And we are going to take two particular values for t to find the sign of the phase difference. The first particular case is for t equal to 0. Then the expression of the voltage becomes equal to Rim sine 0 plus L omega Im cosine 0, which is equal to UBM sine 0 plus phi. That's mean the equation becomes L omega Im equal UBM sine phi, which represent equation 1. For t equal pi over 2 omega, Rim sine pi over 2 plus L omega Im cosine pi over 2 equal to UBM sine pi over 2 plus phi, and the equation becomes equal to Rim, since sine pi over 2 equal 1 and cosine pi over 2 is equal to 0. So Rim represent the first side of the equation, and at the second side UBM sine pi over 2 plus phi. So equation 2 is equal to Rim equal UBM cosine phi. Divide the two equations on each other to obtain L omega Im over Rim equal to UBM sine phi over UBM cosine phi. So after reducing, the equation becomes equal to L omega over R equal tangent phi. So using the equation of tangent phi equal L omega R, and for R different than 0, we can conclude that phi is different than pi over 2, and for L omega over R different than 0, phi is different than 0 radian. So for L omega over R greater than 0, then phi is between 0 and pi over 2. So the phase difference of UB with respect to I is between 0 and pi over 2. So we can conclude that the phase difference between I and UB across a coil is pi over 2 when the coil is purely inductive, and between 0 and pi over 2 when the coil is resistive. Conclusion: When a coil of inductance L carries an alternating sinusoidal current of angular frequency omega and of amplitude Im, the voltage across the coil is alternating sinusoidal of the same angular frequency omega, and the voltage across the coil leads the current pi, a phase difference between 0 and pi over 2 if it is a resistive coil, and by a phi equal pi over 2 if it is purely inductive coil. And the maximum voltage or amplitude across a purely inductive coil is Um equal L omega Im. Summary. 1. In RL circuit, the voltage and the current are always out of phase. 2. In RL circuit, the voltage across the coil leads the current by phi equal pi over 2 if it is a purely inductive coil. And in RL circuit, the voltage across the coil leads the current by phi between 0 and pi over 2 if it is a resistive coil. This is the end of part 2. Study well and thank you for your attention.